Hi everyone, welcome to the second session on practices with gate-based quantum computing 2. Um, we will jump right into the definition of the QAOA, but firstly let me note that all my classes will be structured this way, so you will have several videos, each one for one of the sections of the class. So this way, if you have any doubt or you wanna come back to any video afterwards, it's easier for you to not have like a full 1 hour or whatever duration video. You just have like little bits of information. So yeah, let's go to the definition of the quantum approximate optimization algorithm from now on, QAOA. So as I'm sure that you've seen before, optimization problems are all about minimizing or maximizing. Um, every optimization problem can be a minimization or maximization problem. Why I'm saying both of them? Because when you're trying to minimize one quantity, you can also model it mathematically and also for your problem to be understood. Um, the other way around. So if one quantity needs to be minimized, if you express that in an equation, in a mathematical expression, and you just add a minus sign, you just get the maximization part. When trying to minimize one equation, you just have to add a minus sign in front of it. So this is pretty basic, but just for all to be, because we will be talking about minimizing or maximizing either way, we just know that which is the quantity that we want and what do we want to do with it in concept. Then afterwards, mathematically, we just express it one way or the other way, and we just need to be consistent. So from now on, that will be the case. So when we are talking about quantum approximate optimization algorithm, um, this approximate optimization is finding an approximated solution to a combinatorial optimization problem. I'm sure you've seen before other combinatorial optimization problems. Um, they are well all about optimizing. For example, portfolio optimization is the most common one for quantum. Um, you can solve or approach all of them with QAOA, but you will have always an approximated solution. You won't have the exact one. There's a limit where you could have that one. We will see it in a bit. So jumping into the QAOA, to define it, we first need to remember the quantum adiabatic theorem. I know that you have seen this before in other classes, but let's uh, see at least refresh a bit that concept. So it ensures that the quantum system that begins in the non-degenerate ground state of a tiny Bethlehem Hamiltonian will remain in the instantaneous ground state provided the Hamiltonian changes sufficiently slowly. So what does this mean? That means that if we have a system um, and that system begins in the lowest energy state um, of a Hamiltonian that is dependent of time, so it's changing through time. Um, if you change the Hamiltonian really, really, really slow, um, the system will continue to be in that ground state, in that lowest energy state. Um, this way, we will have to work with two Hamiltonians. There will be the mixer one and the coast one. Um, Both of them will be necessary for us to get to the mathematical expression. We will see this in a minute. The mixer one refers to the Hamiltonian in which we begin the adiabatic process. So refers to the Hamiltonian where our system starts. It refers to a Hamiltonian where our system will be in the ground state from the beginning. And the coast Hamiltonian is the one where we are trying to go. So the coast Hamiltonian will express the function that we will maximize or minimize. This one is the one that encodes the problem. This one is the one that we want to solve. So we must try to go from the mixer Hamiltonian to the coast Hamiltonian. And when we arrive to the coast Hamiltonian, we will be in the ground state. So in that ground state, we will have the solution to our problem. This is the what we will be doing with all of this. So if we have an eigenstate of Hm at the beginning and we go really slow, we will finalize the process in the eigenstate of the corresponding energy level of the coast. Let's say at t equal t. This will be the evolution will have. We will go from 0 to t. So the adiabatic means really slow. That's the condition that we have. So we will see what really slow means also afterwards when we see the why we are finding an approximate solution and not the exact one. So the general expression for a Hamiltonian that is depending on time that we use from the quantum adiabatic theorem is this one. Here you can see that if when t equals 0, that is the when we start the process, the H we will be the Hamiltonian that we will have will be the mixer, and when we finalize it, as we've said, the Hamiltonian will be the coast one. So from 0 to t, we are converting the mixer one to the coast one, and finding that eigenstate will be equivalent to finding the solution that we have. Okay, so how are we going to implement this? So we implement this as a layerized variational method based on trotterized adiabatic process. What does this mean? We are finding approximate solutions. When we are talking about trotterization, we are talking about successively applying a quantum gate that approximates the time evolution of a system for a time slice. So we are dividing in time slices this 0 from t evolution. We're dividing it in time slices. And in each of those time slices, we're repeatedly applying one quantum gate or one set of quantum gates. So variational, the part of variational is because this whole process will depend on some parameters that will be continuously optimized. So each of those time slices, we will apply the quantum gates. Those will depend on some parameters. Those parameters will be updated from the next for the next time slice. We will optimize that one. We will run the circuit again, and that way it goes on and on until we define as far as we define it. So that's why it's layerized. We have several time slices, variational method, and based on a trotterized adiabatic process. So we try to emulate an adiabatic process, but why is it approximate? As we said, because that slow evolution will depend on how many time slices we get from 0 to t. So yeah, we will not be evolving our system but we will do something similar when applying consecutive layers of unitary transformations to the system. These transformations depend on some parameters. As I said, we will call them gamma and beta. You will find some literature with other Greek letters. This doesn't matter. And they will differ from one layer to the following one. So we will optimize in between the layers to get to the optional solution. The more layers, the slower, because we will be dividing the same period of time in more time slices. So we will be um, evolving the system slower. So the more layers, the more similar our solution will be to the real one. So the less approximate will be. So how do we solve this? How do we go through the QAOE? What steps does this have? So we define the coast Hamiltonian first of all, because this one will be the one that encodes our problem. So this one will have the solution when we find its ground state. We also define the mixer Hamiltonian. So because this Hamiltonian will be the one where our system will start. Here QAT means quantum adiabatic theorem. We define the respective unitary transformations that are dependent on the parameters. Each one of them refers to one of the Hamiltonians, and each one of them depends on one of the parameters that we are gonna try and optimize. Then we prepare, as always, an initial state that will be the superposition of all possible states. We choose the number of layers that will mean the number of time slices, so the velocity of our evolution. Of course, it has to be at least one. And that will mean that those are the times that these operations, the unitary transformations that we have defined before, will be applied successfully. So the formula that you have there is the combination of both transformations. First, the mixer one will be applied. Afterwards, will be the cost one. We just apply them consecutively. So in their operational form, we will be multiplying all of them. How many times? The times that we've defined as n, or the number of layers. That would be the circuit. We just apply u that is depending on gamma and beta. That is the consecutive transformation of the system. We use classical methods to optimize the parameters, and then we just measure to get the solutions. And they will be optimal if they maximize, of course, the expectation value of the coast Hamiltonian. So what are the maths that are hidden behind all of this? So if we start with our objective function that we will call, as it's the cost function, we can call it C of Z. We will want to find the value Z that maximizes or minimizes the value of the objective function. Again, maximization, minimization. So the best solution for that problem is the eigenstate with the largest eigenvalue of the coast Hamiltonian. That's our solution. Therefore, for any quantum state, of course, that value of C must be equal or greater than that expectation value of the coast Hamiltonian. Finding the optimal solution of the original combinatorial optimization problem is equivalent to finding an eigenstate with the largest eigenvalue. We have already said that. Now what we want to find is, okay, we have that definition. Let's jump to the definition of the unitary transformations. So the unitary transformations for any Hamiltonian, um, depending on some parameters, are expressed like that. So they are expressed as exponentials. If any of you have any doubt on how are we getting to this expression, you will have the bibliography, one paper where it comes deduced with all these steps. So if we apply this in a layerized process, as the one that we have defined before, the parameters will have one value per layer. So we will have one value of gamma, one value of beta per layer, per application of the transformations. Then we will optimize it, they will change, and then we will apply them with the unitary transformations again, etc., 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 for n layers. On each of them, we will apply both unitary transformations, alternatively, and n times, of course. So we can define that ket, that is gamma and beta, that would be the application, the several times application of the unitary transformations, depending on each of the parameters, or each of the values of the parameters, to the initial state. So we would have an energy value that would depend on those applications, and those applications apply to the applying also the coast Hamiltonian. So that would be the expectation value of the coast Hamiltonian would be that energy value, and the maximum value of that will be our solution under a given number of layers, of course. So we have reduced an initial problem of minimizing or getting to the optimal value, to finding a set of gamma and beta that maximize that quantity, E depending on n. When we get to this point, we already have the definition of our problem. So the only thing that we have to note beforehand, that is that there may be no parameters such that it equals the optimal value, the ideal solution. Why? Because we are approximating to n layers. If we really had a slow and continuous evolution through the time, and we didn't make that approximation on, okay, I'm gonna evolve the system in layers, we will get an approximate solution. So in the limit where the number of layers is infinite, we would have a continuous evolution, and that would mean that we would have the optimal one. So in the next video, I will explain the max cut problem. This is one of the many examples of application of the QAOA, and we will go through the definition of the problem, how can we solve it, and we will also solve it. I will share my screen and I will be coding a bit, so we can see how can we solve it with an IVN solver. So yeah, thank you for watching this, and see you in the next section.